Okay, great. So this is our third meeting, and we are stepping into the third chapter in this course on diffusion models. And today we will actually meet diffusion algorithms, but it will take a while because we will start by talking about the score function first. We'll see how to compute it using denoisers. We'll see how to deploy these in algorithms such as RED and plug and play, and only then get to the actual thing, which is Langevin dynamics and diffusion models. So it's a long chapter. I'm not sure we will cover everything today. We'll just go with it and see how it goes. Okay. So let's all say hello to the score function. Let's see what it is. I remind you, we discussed a lot the idea that if we knew P of X, the probability density function of images, we could have done great things in image processing. At some point, we diverted from this and shifted our focus to the issue of sampling from P of X by a learned machine, G theta that translates a random vector like a pure Gaussian noise into a good-looking image. And now I'm going to add another ingredient to this story. In fact, something that will serve as the bridge between them. This will be the score function. So we have a triangle here, and this is the score function. What is it? It's basically an expression over the function P of X. So it's not P of X, it's not log of P of X, it's the gradient of that. I remind you, P of X is the function that gets an image and computes some sort of probability for it. So it reduces to a scalar. Log of P of X remains a scalar, and the gradient with respect to the input X turns this back into a vector. So what kind of vector is this? Well, what is this expression, and why is it at all interesting, and how is it different from knowing P of X? So let's talk about this, and let's give a little bit of intuition about this score function, okay? And the first intuition I want to draw your attention to is the fact that if P of X is a function that has valleys and hills and valleys, basically of low and high probabilities, then log of P of X looks very similar because log is a monotonic function. So a peak in P of X will be a peak in log P of X, etc. So the gradient is basically a vector that points to the direction that goes the fastest to the nearest peak, basically climbs the fastest. So if this is in 2D, an illustration of P of X, where this is a peak and this is a peak and this is a valley, and you put me here, the gradient of log of P of X points to the direction that goes up the hill in the fastest possible way. Okay, what does it mean? It means that if you put me here and I go along this direction, I'm turning my image into better and better looking image because I'm increasing its probability. Great. So how relevant is this score function? Let's start with a simple illustration just to show that it is relevant. And I'll take you back to inverse problems. And so here is the illustration I would like to create. Imagine again that there was a good looking image X naught. Multiplied by C, and with additive noise, we get the measurements Y. From Y, we would like to return to X naught. So we looked at it a while ago, and we saw that the map estimate, which is yet another way of practicing the Bayesian approach, the map estimate is all about minimizing this expression. What is it? It's a least squares that says, give me the X that minimizes this expression, but hey, serve this expression as well. This is the regularization. And actually, it makes a lot of sense if you look at it, because it says, I want X such that if I degrade it, it will get close to Y. But hey, make sure that its probability is high. Because if probability of X is high, log of probability is high. And with a minus, it means that when I'm minimizing, I'm actually pushing towards more and more probable solutions. Okay? Now, this is an expression which is practically a dead end. But imagine that you would have had an access to the score function. What then? Then, for example, I can minimize this expression by steepest descent, basically taking the derivative and iterating. Look, here's the derivative of this expression. C transpose Y minus CX comes out. And here I have the score function, the grad of the log of P of X. So basically, what I'm telling you is that if I had access to the score function, I could have solved all the inverse problems, all of them that correspond to any C, and getting the map estimate. This is great to know. So score function, if it is available, can serve in those problems. Lovely. Can it serve sampling? Can it actually serve sampling? Yes, this is exactly the story of this course. The score function will be used later on to build algorithms that will sample from P of X. So definitely yes, but it will take a while to get there. By the way, remember that sometimes we can write P of X in a Gibbs form like that. Some sort of normalizing factor with a partition function times exponent of minus some energy function. And oftentimes we replace our focus from P of X to rho of X, the energy that sits here. Well, if you look at the grad of the log of P of X, what is it? You take the log, and of course you get log of Z with a minus sign, minus rho, and then you take the gradient with respect to X, and the log Z drops out, and you remain with this expression. So the score is nothing but the gradient of rho, the gradient of the energy function up to the minus sign. Where is the partition function? Vanished. And why am I so happy? Because we hate the partition function. It's a nightmare to work with it. And so anything that can bypass it is embraced warmly. And this is exactly what energy-based models often do. They go to the score function because they want to avoid the choice for Z. Okay, good. So the question now is, great. The score function can help. How do you compute it? Let me show you in 3 slides a derivation that will actually show you that the score function, as opposed to P of X, is something that you can have. It's something you can actually put your hands on. So let's see how it works. So what I'm going to show you is an old result, 80 years old result, taken from a paper by Miyazawa, a well-known statistician from Japan. And here is what he developed. He said the following. If X is an image with probability P of X, and you add Gaussian noise to it, okay? Gaussian noise, white, additive Gaussian noise, zero mean, constant standard deviation, you get Y. What is the probability density function of Y? Let me stop here. Let me give this question to you. What do you think? What is the probability density function of Y? PDF of X is P of X. What is the PDF of Y?
Convolution with a Gaussian, isn't it?
Wonderful. Exactly. So let's show that, and let's explain how it will help us. So here it is. Probability of Y is basically marginalization. It's the probability of Y for every X times the probability of that X, and you integrate over all the X's. Why am I doing this? Because P of Y given X is something that we easily know. P of Y given X is a Gaussian, because Y for a given X is simply a shifted Gaussian. You are taking a Gaussian, shifting it by a deterministic expression because X is given, and so Y is a shifted Gaussian. So what you see here is basically this expression. All the yellowish part is P of Y given X. What you see here basically is shifting the Gaussian around X. The sigma is the same sigma as the noise. And this is exactly what you said. This is exactly the convolution of P of X with a Gaussian. Not any Gaussian, the Gaussian that defines the noise, okay? Let's denote it as P sigma of X from now on. This will be our blurred version of the probability density function Px. This by itself is a lovely property, and we will have use to it later on, much later on. But at the moment, put it aside and let's proceed. Let's take this expression now. Look at it, this expression. And let's take its derivative with respect to Y, okay? So I'm taking derivative of both sides with respect to Y, grad Y. So this will be gradient of Y of Py. And this will be a gradient of Y that steps into the integral and takes derivative of this. And this is very easy because the gradient of an exponent is simply the derivative of the exponent term times the exponent itself. So let's see. Here it is, coming soon. Let's see. And here it is. The derivative of P of Y with respect to Y. I stepped inside, took derivative of the expression in the exponent. So it's basically Y minus X without the square and divided by sigma squared. So this is why we have sigma squared here. And X minus Y steps out. That's it. That's it. This is the derivative. So I'm coming back to this explanation. Let's see. I'm taking derivative of this with respect to Y. So derivative of the exponent here with respect to y is, because of the minus sign, it is x minus y divided by sigma squared. And then everything remains the same. So this is exactly what you see here, x minus 1 divided by sigma squared, and all the yellowish part is untouched. Now I'm returning to the fact that the yellowish part is p of y given x. Let's write it down. Here it is. Lovely. Now let's take this expression, shift the sigma squared to the other side, and divide by py. I'm dividing by py. Okay, dividing by py, and I'm getting grad py divided by py times sigma squared that moved to the other side equals integral of x minus y times p of y given x times p of x divided by p of y. Now, help me out here. What do you see? What can I do now? Ideas.
Base.
Base, definitely. This is exactly the base rule. Basically, it tells us that all this triplet together is basically p of
X given y.
X given y. So it is p of x given y because of base. What about this side? What is this? What is the grad of a function divided by the function?
Log.
It's a grad log. It's a grad log. Here it is. Our good friend, the score function, suddenly makes an appearance. Okay, so let's summarize. Here we are looking at this expression. Let's open this parenthesis and see what it says. So it's an integral of x px given y in yellow, and minus y steps out, integral of p of x given y. The blue part, what is it? What is it?
P of y.
The blue part, what do you think?
1.
It's not p of y. What is it?
Just y.
It's 1. It's 1. It's an integral over some distribution. Who cares whether y is given or not? You are basically summing a probability density function with respect to all the x's. It must be 1. Okay? What about the yellowish part? What is this?
Conditional
What is
expectation.
Expectation.
the conditional expectation? Or let's call it in other words. What is it saying? It says, if you give me y, I'm supposed to clean it up. I'm supposed to denoise it and come up with the MMSE denoiser. This is the MMSE denoiser. Okay? So I'm summarizing. This is it. And this is nothing but the MMSE denoising of the image y. Okay? So it's time to wrap up. This is the expression we got. So we have a score function up to a constant sigma that you can divide by. The score function of the noisy image y is basically take the image and denoise it and subtract the image. So basically it's minus the noise that I'm estimating. Okay? Minus the noise that is estimated from the image y based on the MMSE denoiser. So score function is definitely within reach, but hey, for noisy images. What about clean images? The sad news is, we cannot compute the score for noisy images, but actually we don't really care for reasons that will be clear later on. So we will always assume that our images are slightly noisy at least. And so with a little sigma and beyond, we are okay. We can compute the score. Okay, lovely. And how do you do it? Plug your MMSE denoiser, apply it on the image y, subtract from the image, get a residual. This residual is basically the minus of the noise that you estimated. And that's it. Okay. And by the way, intuitively speaking, it makes sense, because if there is a manifold of good-looking images and you throw me away by adding noise, by minus the noise, I'm making my way back to the manifold, which is exactly what I told you in order to climb the hill, in order to get to good-looking images. So this is the intuition here. How do you get an MMSE denoiser? What do you think? Can you get an MMSE denoiser? So the answer is written here. Apparently not, but you can get close to it. You can actually train your denoiser to do it the best it can and just plug it as if it is sufficient and forget that you have done something not perfectly exact. We'll talk about it later on. So the bottom line, if you have a pre-trained denoiser or pre-designed denoiser, you are well equipped to compute the score function, which is so much different from knowing P of X. P of X is nightmare. Grad log of P of X is something we have access to. Okay? So let's talk about image denoisers, because clearly they are central in everything that we will do. And let me tell you, we will see a lot of variations of diffusion models later on, and we'll do miracles with them. Miracles. We will create images that you would not believe can be produced. In all those algorithms, inside sits a denoiser. So let's talk about those denoisers. Okay. So we are discussing image denoising, and more specifically, we are discussing denoisers that are supposed to remove white additive Gaussian noise from the image. Basically, this is the denoiser. It gets a noisy image and cleans it up. It knows the sigma, the level of the noise. And my assumption here is that the image itself is the sum of clean image and a realization of Gaussian noise of this form. Zero mean, IID. Sigma is the standard deviation. Okay, now why Gaussianity? Clearly because of the score function that we saw, but in fact, there are other reasons to consider the Gaussian regime, and we'll see that in a minute. One thing that should...
Mickey,
Yes, please.
the score function doesn't work if I have a noise of other sorts other than Gaussian random noise?
At the moment, no. The noise, it has to be Gaussian. And over the years, people invented all sorts of extensions of the score for Poisson or others, but the most natural choice is the Gaussianity. Okay, and no, it doesn't work with other noises unless you are going through a lot of efforts. So let's proceed. One thing I want to highlight here is the fact that image denoising is not trivial. Image denoising is a really tough problem. Why? Because you see, when I have this noisy image, I can always come up with a filter that will remove the noise. In fact, go and multiply the image by 0. The noise is removed. Clearly, this is not enough. Why? Because I'm trying to come up with a filter that will devastate the noise while not touching the content, leave the image almost intact. And this is tough. You know, here is a way of explaining how tough it is. Imagine that I'm giving you a number, 17, and I'm telling you, listen, 17 is a sum of 2 numbers. Please tell me who are the 2 numbers. Of course, this is an ill-posed problem. How come there are infinitely many possible pairs of numbers that can join to 17? Well, this is exactly what we do here. I'm giving you this image, and I'm asking you, who are the images, the clean image here, and the noisy image here, such that, and the noisy image here, such that their sum is the image I've given you. There are infinitely many possible such separations, and we are all about separating such that this will make most sense as a natural image, and this will make most sense as a Gaussian noise image. And this is really, really tough. The task of image denoising is far from being trivial, but hey, it is solvable. Over the years, there were thousands, 33,000 papers to be exact, thousands of papers that were published on the problem of image denoising. 33,000 papers. And look, the graph shows almost a consistent growth. You might think that the last year was somewhat a change of trend. No, it's not. It's just that Web of Science is always delaying in reporting papers. So basically, it will look like this. Okay. One thing I would like to draw your attention to is this blip here in 2010. Suddenly in 2010, people started losing interest in image denoising. We'll talk about it. Okay, so many papers. By the way, more than 95% of those papers dealt with removal of white additive Gaussian noise from images. Okay, so this is the most popular problem being looked at. So what are those papers doing? Obviously, coming up with all sorts of algorithms or analyzing theoretically all sorts of things related to it. These papers are coming from everywhere. They are coming from China, United States, India, Germany, France, England, Japan, and so on and so forth. And here we are, number 21 in this list. Not so impressive. Compared to the 10,000 papers we are in Israel, we have published 355 papers. But if you take every one of those groups and compute their citations, the picture changes. First of all, USA takes the lead with a huge margin. Okay, so the papers coming from the US are the most influential. And Israel is somewhere here, number 9. So basically, in fact, I checked, and in terms of number of citations per paper, I think Israel is at the top, okay, which is amazing. Okay, so now why so many papers? Why are we bothering with image denoising? First, because it is a practical problem. Every sensor that aims to create an image is suffering from noise and needs to be denoised. Every sensor. In fact, your cell phone has a denoising algorithm in it. Otherwise, your images would have been horrible. So it's a practical problem. Secondly, image denoising is the front door to image processing. Whenever a new idea is brought to image processing, whatever it is, people are trying it first on denoising to see whether it qualifies, whether it deserves the attention. And only then they move on. So being the front door to image processing clearly means that many visited it in their process of developing new concepts in image processing. And there is a third reason, and you're already seeing a glimpse of it. The idea that this denoiser is in fact an engine that can be used elsewhere. It can be used for other needs. You have just seen it in the context of the score and what we can do with it. So yes, we will highlight this and expand it much more because this will become the center of this course. You take a denoiser and make amazing things from it. This is another reason to be interested in denoisers. Now, let me come back to the Gaussianity assumption. Why are so many papers assuming the Gaussianity? Because when you don't know enough, this assumption makes sense. Because of the law of large numbers, things are tending to become Gaussian if they're combining all sorts of events and behaviors. In fact, if you think about it thoroughly, the more proper assumption for noise in images would have been the Poisson. And I'll tell you why. Sensors of the kind we work with that creates images are basically counting photons. And the appearance of photons, the count of photons is Poisson distributed. The thing is, if you look at Poisson distribution for high counts, hundreds and beyond, it looks like Gaussian. It's a total Gaussian. And if you have low count, like 4 photons, 5 photons, 10 photons, there is an amazingly beautiful trick called variance stabilizing transform, an algorithm called transcomp. You apply it. Basically, you take the data, you apply a very simple operation, something like square root, something simple. And suddenly you come back to the Gaussian regime, which is amazing. So again, we are falling back into the Gaussianity assumption. Another reason to love the Gaussian assumption is the fact that it has a lovely mathematical form. This coefficient times exponent of minus L2 expression, very pleasant to work with. And it does deliver in many derivations. So yes, something that you want to have. And now we are equipped with more insight. And we know that MMSE denoisers for Gaussian noise only are in fact a very valuable tool. It approximates the score. And as such, it can do amazing things for us. So here is another reason to love the concept of Gaussian noise. Okay, so let's go to the bottom line of it. How do you design a denoiser? And here I'll describe things that will sound familiar to you because we have been through this in a different picture, but it will come back and very briefly. How do you design a denoiser? 2 possible answers. The old answer until 10 years ago, and the new one that started something like 10 years ago. So let's talk about the old answer, and we have been through it. It's basically saying, suggest an expression that will capture what images are like. In fact, guess the function rho of x. Guess and then optimize with it. This is the map estimation, just like the map estimation we kept writing. This is the map estimation that says you gave me y. I'm searching for the clean x. X, you are not supposed to be far away from y. This is exactly the p of y given x up to a constant. And then comes the other expression that says, hey, x, be well behaved. Make sure that the energy is small so that the probability is high. Okay, and so obviously by different choices of rho, you get different choices of denoisers, and you can play with it, and all sorts of optimization techniques and all sorts of variations. And this led to an evolution of denoisers over the years. And we have been through this, the L2 based, and the robust statistics, and the wavelets, and the total variation, and other PDE based, and self-similarity, and sparsity, and patch-based methods. And the most recent comers are the low rank assumptions that are performing the best as compared to all the previous ones. And then this evolution stops. It stops somewhere around 2015, 16, even before. And in fact, already in 2010, remember this blip we saw on the graph that have shown that people lost interest in denoising? Already in 2010, people were debating whether denoising is dead. In what sense? Suddenly, people looking at various algorithms that are coming from different conceptual directions are all touching the same performance ceiling. And so maybe we are touching the ceiling. Maybe there isn't anything that we can do beyond. Maybe the field is dead. And so this is a paper that was published by a friend of mine, Pema Milanfar. Is denoising dead? Basically asks, are we touching the ceiling? And the way to answer is to derive a bound on the best performing denoiser to show that we are close or not. In fact, what he showed is that there is still a gap, but he doesn't know how to close it. A similar paper of a different flavor is the paper by Annealed Langevin. Annealed Langevin is a faculty member in EE in the Technion. At the time, she was in Weizmann Institute. A paper she published with Boaz Nadler did the very same thing a year later. Their bound was different. Their message was similar. The idea is, hey, denoising is not dead. There is more than can be achieved, but we don't really know how to get there. And still, for the practitioners like me, the feeling was the field is dead. Why? Because whatever we tried to do, we kept getting to the same performance and we couldn't break the barrier. We were wrong. We were utterly wrong. And you know why. The field today is very much alive and kicking, and you saw the graph. The number of papers published recently on denoising supersedes everything that happened before. Why? Because of the deep learning revolution. The deep learning revolution brought new ways of designing denoisers and better denoisers, ones that perform so much better than the previous ones. But it's way more than that. The deep learning revolution brought abilities that we never had before. Let me give you a few examples. You can take a denoiser that has been trained for natural-looking images. It is working great, and now you bring scanned documents. Okay, scanned documents are not images you trained on. Clearly, you are not performing so well on them. Can you now take the existing denoiser, the given images, just them, you don't have ground truth, and improve the denoiser? The answer is yes. This is adaptation, and you can do that. And you can jump in performance by 3-4 dB sometimes. It's amazing. Another thing, can you design your denoiser to serve other means? Not just mean squared error, pick a scenario. I want to optimize SSIM. I want to optimize LPIPs. I want to optimize something else. Can I? Of course you can. Go ahead and do it. Nothing that could be done before, now it's easily done. Can you design alternatively the denoiser? Can you come up with a different training paradigms? Yes, you can. Can you treat real noise? I mean, here is my sensor. This is an actual problem. Every company has it. They design a sensor. They have noise in it. The noise is not Gaussian. What do you do? Up to 2012, 14, the answer is, I don't know really what to do. Let's come up with a Gaussian denoiser and play with the parameters until we are performing the best. Today, you can actually design your denoiser to serve these realistic noise situations. So a lot of reasons to look at denoising, a lot of reasons coming from the deep learning era, and another thing, the fact that you can leverage denoisers for other needs. Diffusion models, but not only diffusion models. We have seen that the score function relies on a denoiser. So you can actually take a denoiser and make it serve you in other problems. So because of all this, denoising is very much alive today and kicking. So let's ask again, how do you design a denoiser? And now let's give the modern answer, the one that started 10 years ago and slightly before. And the answer, and you know it, it goes like this. You want to denoise images? Start by gathering a large collection of clean images. Add Gaussian noise to them. Add Gaussian noise to them, okay? Why Gaussian? Because this is what I'm fighting, okay? And this is so easy to simulate. So I can get many, many pairs of noisy images, YK, and their clean version, XK. Define your denoiser, chain of mathematical operation that will take you all the way from Y to X hat, the estimated image. And hey, this is a parametric machine with theta as the parameters. And now train the denoiser to make the best effort to denoise the images as best as it can. So what you see here is a typical possible loss where we say, denoiser, please, when you get YK, try to get XK head that is closest to XK in L2 norm. So L2 as the loss, it doesn't have to be. There are many other losses that can be played with. And here is a block diagram that shows what's happening. You're basically taking the clean images, adding noise, creating noisy images, feeding them to the denoiser, and training it so that the output will get as close as possible to the clean images at the very beginning. So easy. And so what am I telling you? I'm telling you basically that 50 years of extensive work and thousands of academic careers and beautiful results on sparse representations and Gaussian mixture models and low dimensionality and low rank and piecewise smoothness, all these things and so much more, and thousands of papers is now being replaced by what? Supervised learning. Supervised learning of a neural net. So what about all this? Nearly obsolete. This is the fair claim. It's nearly obsolete. Today, practitioners in machine learning feel, and they are right to some extent, they don't need to understand image processing in order to do image processing. They can actually train denoisers or any other machines without knowing much about images, and it will just deliver, and it does. Okay, I'm saying almost totally obsolete because of a small thing that will come up in a minute. Okay, is it clear? So this is really devastating. Imagine I spent on sparse representation 15 years of my life developing beautiful theory. We hardly have any use to it today. This is the sad fact. And a new evolution started, a new evolution of papers. It started very hesitantly. In 2012, the first paper, and then another one, and then several years of peace and quiet, and suddenly a burst of papers. What I'm showing you is a glimpse of a few of the many thousands of papers that came. They are published in CVPR and ICCV and all sorts of leading conferences, all the leading conferences that you're familiar with, not just in image processing or computer vision conferences, but also in Europe's and ICML and ICLR, etc. And this is ongoing, and it is still happening, and with a lot of exposure. Okay, and this is ongoing. So the bottom line, getting a well-performing denoiser of the form that you see here, something that will get Y, the level of the noise, and will clean it up effectively, is definitely doable. Okay, it's doable. We know how to do it. Definitely when it comes to relying on deep neural networks, it works amazingly well. What architectures are people using? It started with RNNs. For a long while, it was UNets. Until recently, people are starting to move to transformers, and they are delivering even better results. And in parallel to all this, there is the classic-oriented structures. What do I mean by this? Remember, I told you that all the old results are obsolete, or nearly so. Well, here is an idea that people are playing with, including us. Take an old algorithm that has a clear justification. For example, it relies on sparse representation, whatever it is. You don't have to care what is it. Take this algorithm and unfold it. Basically, spread it as a chain of operations that you are performing on the image in order to clean it up. And now, once you have the chain of operations, free the parameters and let them learn in a supervised way. So you have an architecture that is well justified. It knows what it does, but it is being learned in a supervised way by showing it inputs and outputs and training it end to end. The beauty about such option is that once you finish training it, the flow of computations makes sense to you. You know exactly what's happening. Every parameter has a meaning. Every activation has a meaning. So it gives you a lot of force, and people are playing with it, and sometimes it delivers beautifully. This is known under the name unfolding, and it is being practiced a lot. And so if I'm coming back to the issue of the score function, then if you have a denoiser, you have a score function. I remind you, it's a score function that is computed on a noisy image. Image of level noise sigma goes through denoising, subtracting Y, dividing by sigma squared, and you have access to the score function. Okay? This is not approximation. This is exact. Okay? Here comes the approximation. Here is my question to you. I'm going and training a denoiser. You know what? I'm leaning on a transformer, the best neural net you can think of. I'm designing my denoiser. I'm training it on thousands and thousands of images. And you know what? I'm even using the L2 norm as a loss so that I'm minimizing the mean squared error. Can we refer to this as an MMSE denoiser? What do you think? Is it an MMSE denoiser eventually? What do you think? People, are you with me? I'm training a neural net to become a perfect denoiser. Is it an MMSE denoiser?
It's an approximated. It's an approximation of an MMC denoiser
Why not exact MMSE?
because you approximate on all your data sets, which is not the real distribution on images in the world. But
So basically, implied from your answer is the fact that if I had infinitely many images, this would have been an MMC denoiser. Is it?
Maybe I'm wrong, but this seems natural to me.
Okay.
I think
Yeah.
it's the objective is you are estimating the conditional expectation, right? In when you denoise, I think it should be.
Okay. Other
Because-
answers?
yeah.
Anyone? It's not an MMSE denoiser. I can work on infinitely many possible images, and I will train and I will do my best. And it's not about getting to the global minima. It will get to the global minima of this network, and it is not an MMSE denoiser. How come? What are we missing? What do you think? So let me give you the answer. You see, for something to be considered as MMSE denoiser, it has to be a conditional expectation. It has to be a conditional expectation, which means that there should exist some probability density function P of X. By the way, I'm not saying that it should be the true P of X of images. It should be a function P of X that this is the conditional expectation of it. And when you train a denoiser like that, I cannot guarantee that such a function exists. Okay, you can train a denoiser, and then you can actually prove that there could be any function P of X underlying this denoiser, serving it, making it a conditional expectation. And why? Let me give you a few examples just to illustrate what might go wrong. Here is something we do know. Excuse me. Turns out that if this is a MMSE denoiser, the Jacobian of it must be symmetric. Okay, what does it mean? It means that, look, this is the denoiser. A denoiser is a machine that gets an image of size 1000 by 1000 and produces an image at the output of the same size. How do you take a derivative of such a machine? You take a derivative with respect to every pixel in the input and with respect to every pixel in the output. So it becomes a matrix of size 1 million by 1 million. This matrix must be symmetric. If it is not symmetric, this is not a conditional expectation. Most neural networks will give you a Jacobian that is not symmetric. We are dead. Okay? Passivity. Turns out that denoisers are supposed to be passive if they are claiming to be conditional expectations. What is passivity? We'll see in a few minutes. Okay? So some condition, and these are just a necessary condition, not sufficient. We don't even have the complete list of sufficient conditions. So clearly there are some conditions that such a denoiser should satisfy, and when we train a neural network, we simply disregard that. Here is another question. Yes, please.
Question?
Yes, go ahead.
Why should it be symmetric? Like why? I never. Can you explain a bit more?
It's not immediate, and just to explain how not immediate it is, let me tell you, when we published a paper called DREAD, which I'm about to show in a few minutes, in 2016, we didn't notice that it should be symmetric, and we made a mistake. And this was very much missing in our paper, and then a follow-up paper made an issue out of it. So clearly, it's not trivial. The message is, if this is a minimizer of some function, being a minimizer, it must be symmetric Jacobian. It's a property of differential calculus. Okay?
Nice.
Here is another question. A lovely question. Suppose someone gives you a denoiser. Yeah, okay, it's not MMSE, fine. Can you do something? Can you wrap it somehow and modify it so that it becomes an MMSE denoiser? And remember, I'm not searching for the MMSE denoiser for P of X, the true probability density function of images. I'm referring to MMSE denoiser of a specific P of X, any P of X, that is not far away from P of X, the true one, and this will be sufficient for me. Can we do that? The answer is we don't know. We don't know. Basically, there was one paper that suggested take a denoiser and symmetrize its Jacobian. And this paper, by Peyman Linalfar, the same guy we saw before, it has shown that when you symmetrize the Jacobian, the performance actually improves. Okay, so basically all these questions are wide open. We are stuck. So what am I telling you? I'm telling you that when you apply your denoisers as an approximation for the score function, there is always something missing. You are not really using MMSE denoisers. You're using something related to it. Okay, so just be aware of that. Okay, we are moving to the next chapter. It's a short chapter, and I think we'll take a break now. It is the most appropriate time to take a break. So let me stop the. Okay, we proceed with a short chapter on two techniques called plug and play and red. And you'll see why they are mentioned. They are mentioned because they are somewhat related to score functions and to how they are being used for inverse problems. Everything that will be discussed now serves inverse problems. So let's see what happens. I remind you, inverse problems of the form that look that are presented here: denoising, deblurring, super resolution, demosaicing, tomographic reconstruction, in painting, and many others, are all described as there was a good image X naught. It was multiplied by a degradation operation C that you know. Then additive Gaussian noise came in, and you get Y. From Y, try to recover X naught. Okay, these are the inverse problems we kept discussing, and I'm coming back to them. And what we have just seen, and I'm repeating things we have said, is that for this family of linear inverse problems, we are supposed to minimize this expression in order to get the map estimate. And we saw that by a gradient descent, steepest descent, we take the grad of the expression here. The gradient of the L2 term here is very simple. C transpose jumps out, and practically that's it. And grad of log is the score function. And so, yes, great. If you have access to the score function, then here is the score function. Remember, this is the score function of a noisy image. And so if you want to use it, here is an algorithm that you could use in order to get map estimate. Start by some initialization. This is arbitrary, okay? I'm just doing something in order to come back to the domain of images. C transpose times Y will be my initial image. And then I'm iterating using this steepest descent algorithm. And what changed here? Only this. I'm not working with a denoiser on the clean image as the original expression suggested. I'm using a slightly noisy image, sigma naught, where sigma is so small that it is not something you see. So this is my score approximation. And if you do that, you will have an algorithm that recovers the, here it is. Now a denoiser that removes a level of such noise minus the image itself. Just plug this in your iterative algorithm and you solve inverse problems. This is great. This is fascinating because all the problems I mentioned before are solvable using a denoiser. Listen to these words. Listen to what I'm saying now. You have one denoiser, MMSE denoiser, or at least something that tries to become MMSE denoiser. This is all you have. And with it, you are basically getting the map estimate of all possible linear inverse problems by iterating with this formula, simple formula. This is amazing. In fact, if you want a denoiser that will be the map estimate, you could do this. Simply plug here C equals identity, and you are getting an iterative algorithm that turns an MMSE denoiser into a map one. Okay, if map is what you're after. Great. And just repeating again and again the application of denoising, something like 30, 40, 50 iterations, and you're there. And this idea, surprisingly, has been discovered earlier. Before we knew about score functions in our field, in image processing, and this is where I'm going now with the plug and play and red. Let me show you these two ideas because they are aligned eventually with this equation, but from a different direction. So people ask the following question. Suppose that you are given a denoiser. How can you solve inverse problems with it? And then came the answer by this paper by Charlie Bauman, plug and play, Charlie Bauman and his students. Plug and play priors, a beautiful paper, very simple to read, very easy, published in 2013. The word score is not there. They're not leaning on it in any way. They're doing something entirely different. And I'll present it to you in a second. I was very impressed with this paper. I was very influenced, and several years afterwards, I published together with a friend, Pema Milanfar, and with Yaniv Romana. You might know Yaniv. Yaniv is a faculty in our department. A paper called Regularization by Denoising, RED, something that is a twist over that paper. Both papers are basically saying if you have a denoiser, you can use it to regularize your inverse problem. And it's a solid concept. Let me show you in a minute how it works. And if you dive into the algorithm, it will look like this. You take your measurements Y, you do a simple operation, denoising. Simple operation, denoising. Keep doing it several dozens of times, and you end up with a map estimate. How does it work? Let me show you one slide on the plug and play to understand how it works. So the plug and play says the following. In a second. This is what I'm trying to minimize. And imagine that by some miracle, I have access to the function rho of x, the energy within the Gibbs form of the pile, okay? Imagine that I knew it. In a minute, you'll see that I don't need to know it. Okay, what they said is, let's split variables. Let's do something really dumb. Let's come up with a new variable v that will have to be equal to x, such that this expression remains with x, and this expression is written with respect to v. Now, since x and v are the same, nothing changed. I just complicated something, okay? Now, let's take the constraint here and turn it into a penalty. So here is what I'm doing. I'm saying x and v, you are supposed to be very close by, and I'm giving a power beta to this penalty. So if beta is large enough, x and v will be close to each other. In fact, in the original paper, they did something else, something that you should know of. It's called augmented Lagrange, a terrific technique where they turn a constraint into a penalty without approximation. It's an exact concept. Here, I'm just showing you a simpler version of it so that it will fit into one slide. Okay, so now you have three penalties, two unknowns, x and v. The typical strategy, it's called ADMM, is fixed one, optimize the other. Fix the other, optimize the first, and so on and so forth. So let's fix v. If I'm fixing v, then rho of v is a number. Who cares? So you are optimizing the first and the third expressions. This is it. Looking at it, you say, oh, this is easy. This is a linear system of equations. This is the simple operations I promised you. So it's a simple operation, and I know how to compute x hat if I know all the other ingredients here. Now let's freeze x and optimize with respect to v. Now the first term drops out. I'm remaining with the second and the third. Second and the third. I'm looking at it, and I have a deja vu. This is a denoiser. So the idea was, okay, bring me your favorite denoiser and plug it here. And so you do the simple operation and denoising and keep jumping between the two. And this is the plug and play approach. The plug and play approach is working great, but it has some sensitivities, and proving its convergence is not that trivial, which had many people working on follow-ups to this paper. And here is what we did in the paper called RED, Regularization by Denoising. And our starting point was very similar. This is the expression we are trying to minimize. What do you do? What we did is to suggest a very specific expression for rho. We said, rho, you will be this bluish part. This expression uses a denoiser in order to explain what is the energy here. So it doesn't look like something natural. So let me explain what is the intuition behind this expression. It basically says the following. You know, when you denoise an image, you are essentially smoothing it. You're smoothing it in all sorts of direction in order to remove the noise. So think about D operating on x as s times x, where s is the smoothing operator. So basically x minus d of x is basically identity minus s times x. And we have the x transpose on this side. Now, this expression is quite familiar to us. Identity minus a smoother is some sort of a Laplacian, but this is not a simple Laplacian. This is a very smart Laplacian. Why? Because the denoiser is smoothing differently in different regions based on the content. And so the overall Laplacian here is space dependent. It's actually depending on the content of the image. And as such, it is very smart. So we have here a smoothness term. We are forcing smoothness, but with a very smart Laplacian. This was the idea. And then we got stuck. Why? Because this is a lovely expression, and I want to minimize it. And obviously, I need to take a derivative. Now, if you are going to take a derivative, you are soon discovering that you have to take a derivative of the denoiser. derivative of a denoiser, I remind you again, a denoiser gets an image of size 1000 by 1000 and creates an output of the same size. So the derivative is a Jacobian matrix of size 1 million by 1 million. Excuse me. No one wants to compute such a matrix. No one wants to manipulate it. So what do? So a miracle happens, and you can prove that under some conditions, the derivative of this expression is this. Now look at this. This is the score function, the minus score function. We didn't know. So we prove that the derivative of this is this. And so this is what you have to plug in when you are working with a derivative of the expression. Okay, what are the conditions for this? You have the denoiser has to be differentiable. It has to have local homogeneity. We'll see in a second what it means. It has to be passive, and it has to have symmetric Jacobian. It has to be MMSE denoiser. We didn't know that. Okay, and so, for example, if now I'm using the steepest descent, I'm taking derivative, and now the derivative is pleasant. Remember, now in the derivative, there is no derivative of the denoiser. There is an activation of the denoiser, which is trivial. Here is the expression: simple operations and denoising, just as promised.
Nikki,
Yes.
Question, but D is some nonlinear function. No? You have some gradient.
D
with
is a
respect-
highly nonlinear function, highly nonlinear, but
you have-
differentiable.
Okay,
So
but you have you're missing the Jacobian with respect to x.
No, we'll prove in a second that you don't need it.
Okay.
We'll prove it. This will be the next slide. And so this is what we got. In fact, something else happened here. Under those conditions, especially the passivity, you can actually show that the bluish part here is a strictly convex function. And being a strictly convex function means that the overall expression here is convex, and then you get to the global minimum with these iterations, which is amazing. So you get the map estimation, and it is unique. Great. Let's prove this. It will take us a minute or 2 minutes. So here is the theorem. Basically, if you have a denoiser D, and it is differentiable, and it satisfies the following properties: local homogeneity. Local homogeneity says if your denoiser works on the image X multiplied by alpha, and alpha is very close to 1, from above or below, then alpha can go out without any harm. If this is true, then the denoiser is local homogeneous. Second property, passivity. Let me jump the passivity and go to the next property. The next property is the Jacobian symmetry. You take the derivative of the Jacobian, and it is a matrix that needs to be symmetric. The previous condition, strong passivity, means take that Jacobian, which is a symmetric matrix. It has eigenvalues. It has a spectral radius rho. This is not the rho that we saw before of the energy. This is the spectral radius. It has to be smaller than 1. That means all the eigenvalues are between -1 and 1 without touching the borders. Okay, so this is the passivity. And if this is all true, then this energy function that I've written has a derivative. Here it is. This is the derivative. It doesn't have any Jacobian in it. And secondly, it is strictly convex. The proof is very short. It goes like this. Here is the expression I'm trying to take derivative of. This is it. Okay, I'm opening it. It's derivative of x transpose x and derivative of x transpose d. Now, x transpose x, derivative is 2x, very simple. This derivative is basically a derivative of multiplication. So it's a derivative of the first times the second, and derivative of the second times the first with a transpose. These are the rules in vector calculus. So here it is. Derivative of this is 2x. Derivative of this is the first time I'm taking x as derivative, so it's just falling out and I'm remaining with d. And then it's derivative of d, this is Jacobian, time x transpose, and transpose on everything, so this is it. Now let's rely on the fact that this is symmetric. Here it is. So it's symmetric. What is this expression? What do you think? Are you familiar with it? There is a function that operates on x, and I'm taking its gradient and multiplying it by the direction x that is what fed to the function. What is the name of this expression? People? It is known as directional derivative. When you take the function d and you compute the derivative in direction x, so basically you move epsilon in direction x minus d of x divided by epsilon. This is a one-dimensional derivative of d in direction x. This is known as grad d times x. Now, use the homogeneity. 1 plus epsilon comes out, and you end up with d of x. So all this is nothing but d of x, and here we are getting the derivative that was promised. Now, as for the passivity, it's very simple. If this is the first derivative, then the second derivative, the Gaussian, is 2 times identity minus the Jacobian. Now, if this Jacobian is symmetric and has eigenvalues smaller than 1, then all the eigenvalues here are always non-negative. In fact, strictly positive. The Gaussian is positive definite matrix, the function is convex, and we are done. So this was the red algorithm, and the red algorithm works great. Let me show you, plug and play and red. What you see here is a very blurry image. This is the ground truth. And what you see here are 4 restoration results. NCSR is a great performing algorithm that was designed for deblurring and super resolution. That's all. This is what it knows to do, and it is designed delicately for these 2 problems, and it performs well. This is the result that we get here. What you see here are 2 results for plug and play and red that never knew that they are going to work on deblurring. They just take an existing denoiser called TNRD and use it iteratively. And look, the results are competitive and even better than the NCSR. This result here is even more strange. What we did here is to take the algorithm red and plug a denoiser that is the dumbest thing you can do, a median filter. Median filter is not even a Gaussian denoiser. It works. Not so great, but does work. This is a sharper image of this. And for super resolution, it does deliver as well. This is a bicubic interpolation of the image. This is the plug and play. This is the plug and play and the red using the TNRD. And this is the NCSR that I told you about. And plug and red here is doing even better than NCSR. The results is sharper, crisper, etc. Over the years, there were many citations to this paper, many follow-ups. People analyzed theoretically convergence properties of these 2 algorithms. They deployed it to different applications, and they create new variants of these. But what I like the most is the concept of unfolding. Again, unfolding. Think about the following. Take, for example, the plug-and-play algorithm. Imagine that you are interested in coming up with a single neural network that will solve all inverse problems together in one shot. Remember, I can always train a neural network that deblurs images. Simply give me a neural network like UNet. I will feed a blurred image, expect a clear image at the output, train on many such pairs, and I will get a single machine that deblurs images. But then if I want to solve another problem, like in painting, I'm stuck. What if I could come up with a machine that does it all, solve all inverse problems? Here's what I'll do. I'll unfold 10 iterations of the plug and play, where the operator C and C transpose appears there, and 10 times, then 10 times the denoiser appearing. And now I have a very wide network, and I will train it on many inverse problems by replacing C. Many examples of super resolution, many examples of in painting, many examples of blurring, etc. And now I will train the machine. Training means what? I will allow myself to change only one thing, the denoisers. I will actually tell the denoisers, listen, you are being used to serve other problems. Adjust yourself. So people did that, and it works amazingly well. And now you have access to neural networks that can solve a family of inverse problems, not just a single one. This is something that I really like, where the classics comes and helps the more advanced techniques in deep learning. Okay, we now shift gears and move to diffusion models, okay? So brace yourself and let's start. Let's talk about Langevin dynamics. We saw this triplet, knowledge of P of X, sampling from P of X, and the score function that we can approximate and has a relation to the other 2 in some way. We discussed heavily the 3 corners of this triangle. And now I'm coming back to the main question. Suppose that someone gives you P of X. Listen carefully to what I'm saying. Suppose that someone gave you P of X. How can you come up with an algorithm that samples from it? Samples fairly, that means creating samples that their empirical distribution is P of X. Basically, I'm asking, how do you design G theta? Okay? Because if I know how to sample, then I'm answering G theta. What I'll show you now in a few slides is that answering this question amounts to using the Langevin dynamics, which we will see in a minute, which uses the score function. So the score function is the bridge between the 2. Knowing P of X, or basically knowing the score function of P of X, can serve you in sampling from the distribution. How? Let's see how. So this is the person, Paul Langevin, French physicist, famous, who lived, roughly speaking, 100 years ago. And he did a lot of work. Most of his work was concentrated on modeling the dynamics of molecules in fluids. Essentially, this means that he was more of a mathematician than a physicist because he was playing with specific constructs of math known as stochastic differential equations. And so with stochastic differential equations, something that we will see in a minute, he defined a Markov chain Monte Carlo technique that essentially answered the question of how molecules are moving in fluids over time. Okay, so I have here three terms: stochastic differential equations, Markov chain, Monte Carlo. Let's talk about each and explain in one word what each means. Monte Carlo is basically the general name given to a wide family of algorithms that are random by nature, but they are coming to solve a numerical task. Let me give an example. Suppose that you are looking at a shape in 2D, a bizarre shape, and you want to know the area of the shape. Here is an algorithm based on randomness that will enable you to compute the shape. Take a square that contains the shape, and now you know the area of the square. Draw at random, uniformly, points in this square. This is easy. So you draw at random points in this square, and per each point you ask, are you inside or outside? Count the relative number of points falling inside, and as the number of such random choices grows to infinity, you are getting a very good approximation of the area of the shape. What have we done here? We are solving a deterministic problem with a random concept, a random algorithm. This is the Monte Carlo approach. Why is it called Monte Carlo? Because Monte Carlo is a well-known city where there are many casinos, and so we are playing a casino here in order to solve a problem. I hope this is clear. We will see Monte Carlo algorithms emerging in a few minutes. Markov chain is something we discussed. Markov chains refer to a sequence of random vectors that are connected between themselves in such a way that every vector is dependent statistically only on the previous one, not on the predecessors. And so, again, you will see Markov chains playing a central role in whatever we will do. And then stochastic differential equations. Differential equations, you know, these are equations where functions and their derivatives are appearing together in an equation, and you have to solve for the function. When the differential equation is stochastic, it really means that it has also noise in it, or random entities inside. So we will see now such SDEs. In fact, SDEs are central to this field of diffusion models. And I remind you that Noam is supposed to give us a complete lecture on SDEs and ODEs and their role in diffusion models. It will come at some point in the course. Okay, so let's move on to the main message by Langevin, the Langevin dynamics. Imagine that there is a probability density function P of X that you would like to draw from. Paul Langevin suggested the following formula for getting fair samples from it. This is the equation, very simple. It's also known as the Ito's equation, and it is a stochastic differential equation. What do we see here? First of all, you definitely see the score function, okay? And this is great because it really means that everything is driven by the score function. In fact, all the rest in this equation is completely simple, okay? The process that is described here in this equation is that X is a vector that evolves over time. It starts at time t equals 0 and ends at times equal infinity. And if by any miracle you happen to have solutions of this expression or equation, if you have solutions of it in t time infinity, then those are the fair samples that you will be getting, okay? Now let's make sense of the two sides here. Xt is the temporal derivative of x. So x of t are the vectors that are changing over the continuum time from t equals 0 all the way to t equals infinity. Xt says take the derivative of x at time point t. The same goes for Wt. Wt is the derivative of something known as the Wiener filter. You'll see here many terms: Brownian motion, Wiener process, random walk. They are all referring to something very simple. And here is the idea. Imagine a process where you start from the origin and you create an infinitesimally long Gaussian vector, IID Gaussian vector, and it goes outside of the origin. And now add another vector like it, another vector like it, another. Keep creating random Gaussian vectors, every one of them independent of all the previous ones, and keep adding them, keep piling them on top of each other, and you will have a random walk that somehow gets away from the origin. This is the process WT. This is the process W of t. WT here says the derivative of it. Now, what is the derivative of it? The derivative is exactly this infinitesimal vector that you added to move from t to t plus epsilon. Okay, so this is the equation. Let me give you a little bit of intuition here, just to have a feeling for this equation. Imagine that this is missing, okay? Imagine that this is not here. What am I saying here? I'm saying as x changes in time, it should go up the hill over the function log of p of x. This is exactly steepest ascent. I'm going up the hill. I'm going to the modes of the function, going to the peaks of it. So without randomness here, I'm just converging to the peaks. By adding randomness, I'm perturbing things and I'm basically creating the fair sample. This is the equation that Langevin gave us, okay? If you initialize it somehow, in fact, it doesn't matter how you initialize, then this process at infinity creates a fair sample from P of X. If you do it many, many times, you get many, many fair samples. Their distribution, their empirical distribution will match that one of P of X. This is the core idea. Okay, now nobody can work this way. It's continuum. So let's discretize things, which is exactly what I'm going to do now. This is the equation. Let's turn it into something more practical for us. So here's what I'm doing. I'm taking the temporal axis and I'm breaking it into very small intervals tau. 0, tau, 2 tau, 3 tau, 4 tau, basically sampling. This tau is really, really small. And so from now on, instead of being interested in all the time axis, I'm interested only on the integer multiplications of tau. So derivative at time point k tau is basically xk plus 1 minus xk divided by the distance between them, which is 1 over tau. The same goes here. This is the same equation, okay? And when I say xk, I really mean xk times tau. Lovely. Now let's organize this. I'm organizing it xk plus 1. I'm multiplying everything by tau, so this tau vanishes, and I'm getting tau here. I'm shifting xk to the other side. Here it is, xk, plus tau times the score, plus square root of 2. This tau vanishes because we multiply by tau, but we get square root of tau. Wow, why? Because of the following thing. This difference here, this difference is a Gaussian vector. Its length is exactly with variance tau. This is the winner process. So if the variance is tau, if you multiply by square root of tau, you get exactly that you can multiply by a canonical vector z, and you end up with a proper variance. Okay, this is the equation. Look at it. Again, it's the steepest, forget about this element here, and you are looking at this. This is steepest ascent. You go up the hill over the function log of p, just as promised. Okay. So this is the discrete version of the Langevin. We call it Langevin dynamics. And now I have access to the score function with the denoiser. So I can come up with an algorithm. Let me show you an algorithm. Here it is. So start somewhere with a vector that is just Gaussian. Choose very small sigma because we need it for the denoiser. Apply capital K iterations. Doing what? Doing this, doing this exactly to the letter. Okay. And of course, the score function is a denoiser minus the image divided by the sigma, and you denoise with a small level of noise. You are not sampling from P of X, you are sampling from P of X with slight blur, because this is what you can do when it comes to approximating the score. And you close the loop and you are happy. You have an algorithm here that samples from the distribution. This is the first diffusion model. Don't ever use it, okay? By the way, again, if you remove this part, and I kept saying it, you end up converging to the modes, converging to the peaks of the probability, which is lovely by itself, but not serving our need. We are trying to get fair samples. Great. So we have this algorithm. Will it work? Yes. But here are the conditions. Tau has to be very small. How small? Many papers were written about it. The score function needs to be highly accurate. The denoiser needs to be perfectly designed. And the number of iterations k needs to be huge, hundreds of thousands, in order to make it work. Why? We will see in a few minutes. So basically, it doesn't sound like a practical algorithm. And what we will do later on is to fix it, and we will fix it. It will work well by the time we finish with it, okay? But this is the basics. This is the origin of things. Langevin dynamics as it appears here. Here are two problems as described in a paper by Song and Hermon in 2019. Two problems that will highlight why this algorithm requires so many iterations and why it has hard time converging. The first problem is this. I remind you, there is a manifold of images. It is a low-dimensional manifold surfacing somewhere with a huge high-dimensional embedding space, okay? So in the space of 1 million elements, surface of 1,000, 2,000 dimensions is floating around. So most of the region is deserts. Now in these deserts, and you started with a random vector in the initialization, so basically you are away from the manifold. You are away from the manifold. I'm sitting in a point where the probability is 0. Clearly, the image I'm holding has probability 0. The log of 0 is minus infinity. The gradient of this is God knows what. So it will be something random. It will be something that has no knowledge of where to go. So the gradients you will start with will have no clue where to go. So you will be walking around like crazy, and hopefully with the noise, eventually you will get to the manifold. So this is why we need hundreds of thousands of iterations. We are basically walking in the deserts. So this is one problem. There is another problem. It's a more delicate one. So listen. We are relying on the score function, basically a denoiser. Now we train a denoiser on good-looking images that are suffering from noise that we added synthetically, okay? Now, in low probability regions, that means in regions where the image is not probable at all, we don't have examples of images of this source. We don't have their noisy versions. And so the score is not approximating well. This is exactly what happened here in this demonstration in 2D. This is a case of 2D where the probability density function P of X is basically a mixture of two Gaussians, strong Gaussian here and weak Gaussian here. What you see in the arrows are the actual true score function. These are the directions you have to go in order to converge to the peak here and to converge to the peak here. This is the trained score, which is doing great in this region and nearby, doing great here in this region and nearby, but in the middle, the arrows are wrong. They don't have any clue, and this is just 2D. When you go to 1 million dimensions, there will be regions where your score function will be futile. I mean, not to be trusted. So what do you do? So clearly we have some issues here. Okay, let's talk a little bit about the initialization of the dynamic of the Langevin dynamics. How do you initialize it? So clearly, if you initialize with good-looking images, then the convergence will be much faster to actual images. Yes, but how do you do it? You could, for example, take your training data. I mean, if, for example, I'm creating images from ImageNet, then let's start from the 1 million images that I have from ImageNet and create many, many variations of them. You could. The thing is, you get slight variations of them. And you will not get truly daring samples that are creating bizarre combinations of the visual content that you want to have. So it's not good enough. You have to really choose random initialization. And so the most typical approach is just to go for a simple Gaussian vector. If you want to be slightly smarter, go for the center of the distribution of images and apply something that corresponds to the covariance of images if you have access to it. But honestly, eventually everybody is using this initialization. I have a few small topics to cover before we move on to actual diffusion models. First, I want to talk about the theoretical foundations. You see, we took the Langevin dynamics, the SDE, and we discretized.
Nicky,
Yes.
sorry, can I have a question about the previous slide?
Mm-hmm.
You said if we start the our sample x0 with a random Gaussian noise, like with the mean of the, if you go back to the previous picture that you showed, where we have two Gaussians, then we start at the middle, and then we have the same problem that we did before, no?
We definitely, we will have the same problem. If you start with this, you will have some sort of problem. Remember, you are drawing at random. So if I go to the previous picture here, and these are two Gaussians, and just imagine that the two Gaussian are of the same height, then I will draw something in an ellipsoid like this. So sometimes I will fall here, sometimes here, and it will shorten my path and sometimes in the middle, and then I will use the wrong scores. Yes, definitely. The problems is not solved yet. We are going to solve it soon. Okay, the fact that the score cannot be trusted in desert areas is something we will have to avoid. And we will. And continue. So I want to talk briefly about theoretical foundations. We discretized the SDE. Now the question is, can we trust the discretization to still give us fair samples? Turns out that this question was discussed in literature in the past 10, 15 years. Look at the papers, 2011, 2014, 17, 19, and where in ICML, JMLR, I mean, in the literature of machine learning. Let's zoom in on this paper by Dalalian. Theoretical guarantees for approximate sampling from smooth and low concave densities. So basically, already in the title, you see that he makes an assumption. He says, let me assume that the energy function rho is convex. And why am I showing you this? Because 2 years later, the paper by Jordan from Berkeley and his students said convergence rates for Langevin Monte Carlo in the non-convex setting. So they are generalizing. So let's look at the paper by Dalalian, just to give you a taste of the kind of things that people are claiming. Okay, so this is the Langevin dynamics, and here is the theorem. And the theorem says, choose small epsilon, basically. N is the dimension of the vector generated, basically the dimension of the image. Tau is the step size. K is the number of iterations. Small m and capital M are the smallest and largest eigenvalues of the Hessian of the convex energy function. This is the rho function. Okay, and it has Hessian. It is positive definite, and therefore the smallest and largest eigenvalues are both positive, real, of course, and positive. Then he says the probability of the Langevin dynamics samples and the probability of the true will be not far away, will be epsilon away from each other if K is large enough and if tau is small enough, just as expected. And a lot of work behind the scene here in order to make this theorem work, and some assumptions about the well-behavedness of P of X. So just a taste. So many such papers. We will not dive into this. This is not our course. Okay. Another thing I want to mention, which I find to be amazingly beautiful, is the following. Imagine that by some miracle, I can solve this equation in continuum. So forget about discretization. Now, in the continuum, I'm getting a chain of vectors x from time 0 to time 10 to time 20, 30, 40, all the way to infinity. At infinity, they are basically distributed along P of X. We know that. This is what Langevin promised us, and it is proven. Now, the question is, at time point 10, I'm getting many samples that I created up to time point 10. What is the distribution? Time equals 20. What is the distribution? What is the flow of the distribution over time? This is the question people ask. Okay, so the flow of the probabilities of the probability density function, and people wrote a partial differential equation that looks like this. This is the Fokker-Planck PDE. Look, it is a deterministic equation. What you see here is the 1D version of it, as if X is a scalar. And already it is quite complicated, but this equation shows what happens to the density function P, and it can show you that if you check it, that as you go with T to infinity, you converge to P of T, the true probability, but you also get all the path. And from time to time, you will meet papers that deal with diffusion models that use the Fokker-Planck in all sorts of ways. This is the maximum I will say about it. I think Noam will mention more. Right, Noam?
Not in too much detail.
Okay. Yes. Okay. So, and this is all I had to say here. the concept Langevin dynamics appear a lot in the literature, something like 8,000 papers, but most of them are irrelevant to us. They are all in the context of chemistry and physics, and there is a lot of knowledge there. Imagine how much knowledge is accumulated, and only a small negligible amount of it is being applied and practiced in machine learning. So clearly there is a lot to learn and to leverage from what they have already discovered. This is the number of papers published over the years on Langevin dynamics. As you can see, hundreds of papers every year. And we, the community of signal processing, image processing, and machine learning are contributing a small negligible amount of papers in this in this picture. Okay, so there is a lot to learn here. And now let me move to the last part of this chapter, where I'm actually showing you diffusion models per se. Okay, basically here's what I'm trying to do. I'm trying to fix the Langevin model that we have seen before in order to make it practical. And I'm starting as if from the very beginning. You're given a denoiser. How can you synthesize images from it effectively? So the answer, Langevin dynamics doesn't account for a fair answer. Here are 3 papers that answered exactly these questions. The paper by Song and Hermon in 2019, a follow-up in 2020, and a parallel paper that came from Zora Kotkodai and Eero Simoncelli. The first 2 are from Stanford, and the third is from NYU. The year is 2021, but their paper appeared the year before. It simply was rejected from a conference. Imagine that. And in these 3 papers, they are basically answering exactly this question. If you have a denoiser and you want to synthesize images with it, we have a way to do it. You can think about your denoiser as a projection onto the image manifold. And if you look carefully at the algorithms that they are promoting, very similar algorithms in all 3 papers, it will look like this. You start with pure noise, you do simple operation, denoising, simple operation, denoising, keep doing it, and you end up with a fair sample. I think this should give you a deja vu for read and plug and play, and for a right reason. It has a relation. Okay? How does it work? Let's see. Here is the core idea, annealing. I remind you of the main problem that we are suffering from. In the 1 million dimensional space, there is a manifold, very thin manifold. You threw me away at some point, and I'm trying to make my way back to the manifold in order to sample from it. Now I need some magnet to pull me to the manifold. What is this magnet? What is this force that will push me in the proper direction? Here is what we will do. Instead of working with P of X, instead of working with the original density function, we will work with a blurred version of it. We will blur it. And by blurring it, we mean I'm spreading it now. It has large tails that exist everywhere. And suddenly I can surf on these tails. Okay, this is clear, I hope. So, oops. Just a second. So this is the blurred manifold. It has tails that go everywhere. And now there is a very delicate direction that tells me if you go here, you go up towards the manifold. So how do you blur a manifold? How do you blur a probability density function? What do you think? How do I blur? I'm not working with the probability density function P of X. I'm working with the blurred version of it. How do I do it?
You add Gaussian noise?
Yes, definitely. Instead of working with images X, I will work with noisy images Y. Y equals X plus V. And then we have seen this. Probability of Y is a blurred version of probability of X. This is the P sigma. P sigma that says take your P and blur it by Gaussian or width sigma. This is great. So easy. Basically, what are the implications? Sampling from P of X is tough, but sampling from P sigma of X is easier, much easier if sigma is large. So basically, I'm telling you, let's sample noisy images. This is what I'm saying. Let's sample noisy images instead of clean images. Sounds easy, but who wants to get noisy images? So what do? So we do annealing. Annealing means you get a sequence of such sigmas, very large sigma, so large, in fact, that you don't see any content of images. You basically are Gaussian noise, and you go in a chain of values of sigmas that go smaller and smaller up to the point where you get to sigma L, where sigma L is so small that basically the image is clean. okay? And here is what you do. You start with a very blur version of P of X, and you do several iterations of Langevin, and you get to a reasonable result. You stop, change the sigma, narrow down your manifold, and keep going. Another set of iterations, another set of iterations, and so on. So basically, you are chasing the manifold as it narrows down, always trying to be on the tails of it in a reasonable area so that eventually you get into the manifold itself. This is the algorithm. This is the Annealed Langevin dynamics, ALD. It goes like this. Start with P sigma naught, which is very wide. Apply K iterations. K is 5, let's say. Move to sigma 1. Keep doing K iterations, and so on and so forth. Okay? So if, for example, you have 1,000 values of sigmas and K iterations 5 per each of them, then 2,500 iterations, and you get a good-looking sample. In fact, 1,000 will be enough. This is exactly what Simoncelli in his paper and Song and Ehrman in their papers did. So here is the algorithm. Look, it looks like this. You start with a random vector. It doesn't matter really what randomness you bring. You do L rounds per the L values of sigmas. Per each you do K iterations. So nested kind of iterations. You do the Langevin dynamics with the proper sigma, starting with the sigma 0, then moving to sigma 1, etc. This is approximated using denoiser. And every time you finish K iterations, you take the result, turn it into the initialization of the other round that comes next, and so on. This is the algorithm. Okay? By the way, this score function here it is in front of you. Basically, apply your denoiser with level sigma j. So here you're actually applying denoiser with aggressive noise, because at the beginning the noise is aggressive. So you remove aggressive noise. In every round, you apply the denoiser with the proper noise. So this denoiser has to be smart enough to work with the whole slew of values of sigmas that you might get. Okay, so this is the regular formula for score, and this is what we will have to do with the sigma j here. Okay, so basically every one of those denoisers is taking an image with the proper additive Gaussian noise with this strength of noise, and you need to know how to remove it. I hope this is clear. So here it is in front of you. This is the algorithm. It works. It works well. Several comments on it. First, really, you don't have to use the same tau for all the L's. When you work with the beginning with large sigma, tau can be large as well. Why? Because the function itself, P, is so smooth, it's so blurred, then it is very well behaved, and then discretization can be crude. And so you can choose large taus, in fact, proportional to sigma somehow. And people have been playing with it in order to get faster convergence, obviously. So this is one thing. Secondly, this is almost the algorithm that you will find in the paper by Song and Ehrman. Small twist here, but this is it. 1,000 steps, so K times L equals 1,000, will take you home safely, and you'll get lovely results. If you go to the literature, you might get confused. You would look at this algorithm, and you look at the formulations in the paper, and you will see bizarre things happening. For example, people work from L to 0 instead of from 0 to L. And this happens a lot. So just be careful about notations and don't let that confuse you. Okay, I hope this is clear. So this was the Langevin dynamics in the way that was conceived in 2019, 2020 by Song and Ehrman and by Simoncelli and Zora Kotkodai. I have to be fair and say that already in 2015, there was a paper that did almost the same thing and preceded everyone. But it didn't mention the word denoiser. It didn't mention the word score, which is why I'm not mentioning it here. But I will mention it in the next chapter, where it deserves, because it invented an alternative way of devising diffusion models. So when time comes, I will mention the paper by Sol Dickstein, and you will see that. Okay, let's have another take. Another take that is really crucial because people use the following version and not the previous one. Here is what we did. We created a mixture of image and noise. What have we done? We took the image and added noise in growing levels up to the point where the image drowned in noise. And this is our Ys. People said, rightfully, why are we doing this? Why not do something smarter? Why not create a mixture where, let me just show you what they do. They do this. Y minus alpha times x plus alpha times v. This will be the y. When alpha equals 0, this is x. You start from the clean image. Just like here, when v has 0 energy of noise. When alpha equals 1, you don't have any residual image inside. You remain pure noise. So you go to pure noise. So if I wanted here to move from an image to noise, this is approximate, this is exact. So this seems to be smarter, okay? In fact, if you go to the literature and see how people do diffusion, they don't even use this. They use this formula with the square roots. Why? Because of energy considerations that I don't want to drag here because it will come up next chapter and we will do it anyhow. So look at the case that y equals square root of 1 minus alpha x plus square root of alpha times v. What is the energy of y? The energy of y is the expectation over all the x's and all the v of this squared. And so x and v are independent of each other, so I can open and separate into two parts. So I will get 1 minus alpha times the energy of x squared plus alpha times the energy of v, which is 1. So if the energy of x is 1, I'm getting that this is equal to 1. And this is great, which means that y, the images that I'm creating that are combination of noise and images, are always of the same energy. And so I'm not drifting in the space. I'm standing in the same place in a fixed distance from the origin. So this was the idea of working with the square roots. But for the simplicity of the analysis, let me just go with this choice to show you what it does. So people were playing with this option of mixing noise and images. And let's now reinvent Langevin with this. Basically reinvent annealed Langevin, okay? So this will create a chain of probabilities that are also blurred, but in a different way. Let me show you how. So here it is. What is the probability of y? This is the probability of y given x times probability of x dx, just like before. Probability of y given x, please help me out. What is the mean? This is a Gaussian, right? What is the mean of it? What is the mean of this distribution?
X.
It's 1 minus alpha x. If x is known to me, then the mean is 1 minus alpha x. What is the variance of it? What is the variance? If x is known, this is deterministic. So y is a deterministic vector, y minus alpha x, this is the mean, and the variance is alpha squared. So here it is, writing it down. This is the expression. Now, this expression doesn't look like convolution per se, because x here appear regularly and here with the 1 minus alpha. So let's change things a little bit. Let's write 1 minus alpha x as z. Okay, let's call it z. And I'm changing elements here, nothing to it, honestly. And here's the expression. Now it's y minus alpha, y minus z, and here we get p of z divided by 1 minus alpha, which basically says there is a convolution here between a Gaussian of width alpha and a scaled, or let's say condensed, I'm squeezing the function p. So when alpha equals 0, this is p of x, and this is a delta function, no convolution. Convolution of something with delta is p, so if the alpha equals 0, this probability is simply p of x. When alpha goes to 1, I'm getting here a function that gets narrow and narrow and narrow up to the point where it becomes a delta. So this is a delta function, and this is a pure Gaussian. A Gaussian, canonical Gaussian, convolved with a delta is a Gaussian. So I'm moving to the Gaussian case. So this is the alternative, very similar to what we did before, with a twist, that's all. And now let's see the algorithm. Annealed Langevin dynamics takes 2. So you have a chain of alphas that go from 1, where you start from the real image, and end with nearly 0 value. Why not 0? Because of the score function that doesn't know how to work with 0 values. And here's the algorithm. Initialize randomly, L outer iterations for the L values here, K inner iterations as before. This is the Langevin dynamics with a proper alpha here, okay? that starts very big, like 1, and ends very small, and close the loop, take the final result here and feed it as the initialization for the next round, and that's it. And this is the score. Now you wonder where the scores come from. There is a proof that I will skip, but you can actually prove it very easily, very, very easily. And the score basically says you have to apply your denoiser with level alpha j on the image x, multiply by 1 alpha minus alpha j, subtract x, and divide by alpha j. And this is what you have to plug in here. So this is it. This is the algorithm. And by the way, this denoiser is not the previous denoiser. It's a strange denoiser that works on a mixture of image and noise. It's no longer an image plus noise. It's a constant times image plus noise. And it has to estimate x. This is the denoiser that you have to train. And if you did so, you end up with a great looking algorithm. So I presented 2 versions of diffusion models. There are many other variations on top of them. And we will see next week yet another family of such algorithms that coming from a different direction, the ones that I mentioned coming from the Sol-Diktion approach. Why are we calling them diffusion models? Because the thing that diffuses here is the probability density function that starts with a Gaussian and ends with P of x. It's a diffusion of the probabilities, which is exactly what's happening. Now, I wish I could have told you that all diffusion models share the same rationale, relying on denoisers. They are not. 2 years ago, papers starting appearing, showing that you can actually design diffusion differently without denoisers. And maybe some of you will choose papers that will show us such things. So we will see. And just to clarify, diffusion models are not just synthesizers of images. They can serve other needs. They can, for example, sample from posterior, and suddenly I'm coming back to inverse problems. They can help in compression, all sorts of things. We'll see that. Oh, we might talk about it. And it works. This is a paper that was published in 2021 that basically says, listen, people, diffusion models are better than GANs. This is the year where things flipped. Look, it was not the paper by Song and Herman and not the paper by Simoncelli. Those papers created images that were not so impressive. And then came this paper with all sorts of additional tricks, squeezed much better results. And of course, how do you compare results? Using FID. We spoke about it. So this is a big gun FID, and this is their FID, which is better for ImageNet images. Okay, FID 4.59 versus almost 7. Yes, better images, better diversity, etc. And if you look at Imagen or DALI 2 or images from Stable Diffusion or Midjourney, and we'll talk about them later on. We'll have a complete chapter on these. All these are relying on denoiser, serving as an approximation to a score function, being used iteratively to produce images that are amazing looking. Okay, so this is it. Let's stop here.